This DART Tsunami buoy works because a seafloor sensor measures water pressure thousands of meters down. The clever bit here is converting abyssal hydrostatic pressure directly into ocean surface height. Deep ocean bottom pressure recorders rest on the ocean floor, constantly monitoring the immense hydrostatic weight of the entire water column resting above them. As long-period open ocean waves pass far overhead, subtle shifts in sea surface elevation alter the total pressure exerted on the abyssal seabed sensor. By continuously logging these microbar pressure variations, seafloor instruments accurately detect passing wave signatures long before they ever approach shallow coastal shorelines. This deep seafloor measurement capability allows oceanographers to track tsunami energy across vast ocean basins using real-time hydrostatic pressure data gathered at extreme depths. However, raw hydrostatic pressure readings alone are inherently deceptive because deep sea water density changes noticeably with fluctuating water temperatures across ocean layers. If deep temperature variations alter local seawater density, an uncorrected seabed pressure sensor misinterprets density shifts as actual changes in surface wave height. A sudden drop in deep water temperature increases seawater density, creating a higher hydrostatic pressure reading that falsely mimics a rising ocean surface wave. Relying purely on raw pressure measurements without accounting for ambient temperature would lead to frequent false tsunami alerts or dangerous missed detections. The seabed sensor cannot simply assume ocean water temperature remains static thousands of meters below the surface, where abyssal currents move continuously. To overcome thermal distortions, the bottom pressure recorder performs continuous temperature-corrected pressure conversions directly on the abyssal seabed before transmitting data. Integrated ocean temperature sensors measure thermal shifts, allowing internal mathematical algorithms to compensate for seawater density variations in real time. This temperature-corrected calculation converts raw pressure data into an accurate estimate of true water column height standing directly above the seabed recorder. By eliminating thermal density interference, the recorder isolates genuine sea surface height variations caused specifically by passing ocean wave energy. With reliable water height calculations established at the ocean floor, the system accurately detects subtle surface changes occurring thousands of meters above. The bigger problem was transmitting these vital seafloor calculations from thousands of meters beneath the sea surface up to global emergency warning networks. Physical undersea cables spanning abyssal depths to land stations are extraordinarily expensive, difficult to deploy, and highly vulnerable to deep-sea physical damage.
High-frequency radio waves and satellite signals cannot penetrate thousands of meters of conductive ocean saltwater to communicate directly with abyssal seafloor equipment. Without an effective wireless link through deep seawater, accurate seafloor water column estimates remained stranded thousands of meters below the floating surface. Engineers needed a reliable acoustic communication method to bridge the abyssal ocean gap between seafloor pressure recorders and floating surface relays. The DART architecture solves this underwater transmission barrier by combining a seabed bottom pressure recorder with a moored floating surface buoy. The bottom pressure recorder sits securely on the ocean floor, continuously measuring ambient water pressure and converting it into precise estimated water height. An acoustic transducer mounted on the seafloor recorder encodes temperature-corrected water height estimates into specialized digital acoustic sound pulses. These acoustic sound waves propagate vertically upward through miles of open water column towards the surface buoy floating directly overhead. A submerged acoustic hydrophone mounted underneath the surface buoy receives the underwater sound pulses transmitted through the water column from the ocean floor. The surface buoy's onboard electronics process and reformat incoming acoustic observations into standardized digital telemetry packages optimized for satellite transmission. An onboard satellite transmitter inside the surface buoy relays reformatted ocean observations upward into the GOES satellite network. Orbiting GOES satellites immediately transmit the buoy's reformatted observations down to ground receiving stations operated by international tsunami warning centers. During standard ocean conditions, the bottom pressure recorder operates in a low-power routine reporting mode to conserve limited battery power over long deployments. In routine mode, the system sends scheduled periodic water height updates, providing baseline oceanographic monitoring across extended open ocean regions. Onboard software inside the seafloor recorder continuously analyzes real-time temperature-corrected pressure values against established automatic detection algorithms. When a seismic event generates a tsunami wave train, rapid water column elevation changes break expected background hydrostatic pressure patterns. When onboard software detects a tsunami wave signature, the recorder automatically switches reporting from routine operation to fast event mode transmissions. Event mode transmissions bypass routine schedules, sending acoustic data bursts to the surface buoy at high-frequency 15-second or 1-minute intervals. The surface buoy immediately reformats these rapid event mode signals and streams real-time water height observations continuously through GOES satellites.
Tsunami forecasters receive continuous high-resolution sea height profiles, allowing them to verify tsunami wave generation and predict exact coastal arrival times. After the tsunami wave train passes and ocean surface levels stabilise, onboard software automatically returns the system to routine reporting mode. By integrating temperature-corrected seabed pressure sensors, acoustic ocean telemetry, and GOES satellite relays, DART provides reliable early warning capabilities. This multi-stage engineering system confirms actual tsunami wave generation far out at sea, long before waves ever strike vulnerable populated coastal regions. Viewers must avoid touching, boarding, moving, or relying personally on physical monitoring buoys encountered while navigating open ocean waters. Coastal safety depends exclusively on official public warning networks managed by certified meteorological agencies and local emergency management authorities. Viewers must follow official tsunami warnings and evacuation guidance provided by emergency officials to ensure personal safety during marine hazard events.